Okay. Share. All right, so while you get what you need off of here, right, remember that we're talking about vector spaces. There's 8 properties listed here of vector spaces. These should be familiar from what you've done working with vectors in Calculus 3. For vector spaces, the idea is that we should have some notion of adding the things we're calling vectors, and we should have some notion of scalar multiplication of these things we're calling vectors, right? The idea of a vector space is really motivated precisely by the things we can do with vectors. So we sort of abstract these properties and look at these systems in general. So do you have what you need from here, Chris?
Yeah, I'm good to go.
Good, okay. So for our purposes, right, the set of n vectors, which we're going to identify with our n, is a vector space, right? All these properties that we've introduced are properties that we want our n-dimensional vectors to have, certainly. But this also works for matrices. So set of matrices with m rows, n columns, and real entries is a vector space. So let's think about that. We can add matrices, certainly. We can, we have commutative and associative properties for adding matrices because everything in these operations works entry by entry. There is a zero matrix. There is an additive inverse, and it's just the additive inverse of a matrix is minus the matrix, minus 1 times the matrix. We can multiply a matrix by the number 1 to get the matrix back. A scalar times the sum of matrices, we can distribute that multiplication. Same thing over here. Same thing over here. And we have a, therefore all the properties we need work for matrices just as well as they do for vectors, standard vectors. And one that's a little bit further afield is the set of all polynomials. Of degree n, that's a vector space. Okay, you add 2 polynomials of degree n, you get a polynomial of degree n. And you can check all of the other properties as well. So there's many other examples as well. We'll see some of them in this course. So once we have the idea of a vector space, there's a definition that's important to understand. A non-empty set S, which is in Rn, is a subspace if when x1 and x2 are in your set, then any linear combination, oops, C2, x2, And I'm just gonna put vectors on vector signs on top of these. We're gonna think about this in terms of vectors mostly. So let's just think in terms of vectors. Okay, so essentially what is this saying? If we've got some vector space, so we're thinking of Rn as a vector space. So that could be the set of n vectors. And we have some subset of that whole thing such that we can add, or we can take a linear combination of any two entries in the space, in the set, and we get another entry in the set, right? So we're closed under the process of taking linear combinations. Then we call that set a subspace. And if we go back, right, to the idea of that we used to motivate this, the XY plane we can think of as R2. This line we can think of as a subspace of R2. Any two vectors, position vectors that put us along the line, if we add them, we get another position vector that lies along the line. Any scalar multiple of 2 points on the line is going to give us another point on the line. So we actually have all the properties here. And this is the geometry that you should keep in mind when you're thinking about subspaces. The setting can be much more abstract, but this is really the sort of geometrically what you want to think about. A line that goes to the origin in R2 is a subspace. A line that goes to the origin in R3, or a plane that goes to the origin in R3 is a subspace, okay, because they satisfy these basic properties. Okay, so any questions at this point so far? Okay. All right, so does everyone have what they need off of this second page? All right, so there was a question on the chat. Does it have to go through the origin? And the answer is yes. It must go through the origin. And you can sort of see that from the following. Say x1 and x2 are in your thing you're checking to see if it's a subspace. One of the really the property you need to check is I take some arbitrary linear combination of those two quote unquote vectors. I need to get another vector in my space for it to be a subspace. Well, you can always take these constants to be 0, right? C1 and C2 are real numbers. Well, 0 is a real number. So if I take 0, x1 plus 0, x2, I better get the 0 vector. I better get the origin. Okay, does that make sense? Okay, good. So everyone have what they need here? Okay. So we can relate the idea of subspaces to the idea of span. Oops. Space. Just span. So what's going on? The set S defined to be the span of some group of vectors. And I'll write the vectors with a bar underneath, just because it's easier for me here. So why is this? Well, what does it mean when you're talking about span? The span of the set of vectors is just the set of all possible linear combinations of the vectors. So clearly, whatever this set of vectors is, if I take two entries in there and add them together, right, I'm just going to get another linear combination that lives in the space. So let's say I have this is a vector that's in the span of S, right? An arbitrary vector in the span of S I can get as a linear combination of my vectors. Let's take another arbitrary vector in the span. If I add these up, and I group them by the vectors involved, clearly scalar C1 plus scalar D1 is just another scalar, right? So I add up two distinct linear combinations, I get another linear combination. So that's also in the span. Okay, so the span of a set of vectors is going to be a subspace of whatever space these original vectors, the A1 through AK, live in. Okay, so is that idea clear? Making sense? Okay, so another useful idea. So we've got some set S. It's a subset of Rn. So think of a set of n component real vectors. That's going to be a subspace if and only if we can find a set of vectors such that S is equal to the span of that set of vectors. Okay, so a span of a set of vectors gives you a subspace. If you have something that's a subspace, you know you can write that as a span of some group of vectors. Okay, and does everyone have what they need off of here? Everyone good? Are there any questions so far? Okay. All right, so the null space. Okay, this is a important subspace of a matrix. Okay, so we denote that null of whatever matrix we're talking about And that is defined to be the set, and I'll use curly braces for set. Vectors x such that ax is equal to the 0 vector. Okay, so if you haven't seen this notation for sets before, the vertical bar, or sometimes this is written with a colon, is just read as such that. So if we've got a matrix, right, so here's an example. So we can take the matrix, multiply by a vector. We want to get the 0 vector. So here's a matrix. What's the null space for this going to look like? Well, I can work out a set of algebraic equations for the components of vectors that are going to work here. So 0 times x plus y is equal to 0. 0 times x plus 0 times y is equal to 0. So any vector of the form, notice that any x works, but the y entry has to be 0. So any vector of this form is going to be in the null space of this matrix with entries 0, 1, 0, 0. Okay, does this idea make sense? Oops. Is this making sense? Are there any questions on this page? Okay. So we've got this defined. We're calling it a space. Notice that if ax is equal to 0 vector, a times, oops, and ay is equal to the 0 vector, matrix A multiplied by that linear combination of vectors, that's going to be C times ax plus D times ay. And ax and ay are 0. So notice when two vectors are in the null space of the matrix, any linear combination of them is also in the null space of the matrix. So the null space of a matrix is a subspace. Okay, to be more precise, let's say you have a matrix A, which is in the set of matrices with m rows and columns, real entries. Then the null space of the matrix A is a subspace of what? Well, it's a subspace of Rn, because for this matrix A, it's got m rows and columns. If I want to multiply this matrix by a vector, it's going to be an n component vector. So I can take these matrices, multiply them by vectors in Rn. So when I talk about the null space of this matrix, it's a set of vectors in Rn. Right. All right, so are there any questions on this page? Is this good? Everybody good? All right, so does everyone have what they need off of here? Okay, so let's try an example. Okay, so say we have a 4x4 matrix. Okay, and -3 to -1, -7. Okay. We want to find the null space. Of this matrix. So I'm not going to show all of the work here, but let's get the matrix to reduced row echelon form. If we do that, it turns out that the matrix looks like this. Okay. So the equivalent linear system if we're trying to find the null space for our matrix A, right, notice that, darn it. If we look at A times X equals the 0 vector, we go to RREF form. Let me call this B here. Any elementary row operations we do isn't going to change the fact that we have 0 entries everywhere to the right of our divider in the augmented matrix. Right, so we can look at Bx is equal to the 0 vector. And what we're going to get for our equations, first, the top row is going to give us x1 plus x3 plus x4 is equal to 0. The second row is going to give us x2 plus x3 minus 2x4 is equal to 0. And then we've got 2 rows of only 0. So these are the only non-trivial equations. Notice that x4 and x3 should be free variables, right? We have pivots for x1 and x2, not for x3 and x4. So we'll use a sub h because we're talking about the solution to a homogeneous linear system here, right? What's that going to be? Well, it's something you can actually just read off here, right? So let's say S and T are the arbitrary parameters we introduce. And we've got a 2-parameter set of solutions to our equation. And therefore, the null space is going to be any vector that we can make. Notice we've got a linear combination of 2 vectors already. So this is not the only way to characterize it, but the null space of our matrix is, really the span of those 2 vectors we have here, multiplied by our free parameters.
Can you quickly explain where those column vectors came from on the bottom?
Oh, sure. Okay. So let's just get rid of this for now. All right. So think about this reduced row echelon form. Okay. So we see that we have pivots here. Right. These columns go along with the unknowns x1, x2, x3, x4. Right. So we've got pivots for x1 and x2. We're going to treat x3 and x4 as free variables. So what we're going to do is think about putting, say, x3 is equal to s, x4 is equal to t. Then what's your first equation here telling you? The first line here is saying that x1 plus x3 plus x4 is equal to 0. Right? And what about x2? So it's going to be negative x3, so negative s, plus 2x4, so plus 2t. Okay, so x3 is equal to s, x4 is equal to t. So far, so good?
Yeah.
This is making sense? All right, so we can write our solution. Let me just get a little space here. So we can write our solution in this form. So x3 was s, x4 is t, x1 is minus s minus t. And x2 was negative s plus 2t. And I noticed that I can write this as s times minus 1, 1, 0, plus t times minus 1, 2, 0, 1. Okay?
Okay, thank you.
So in fact, explicitly what we have here is we have the null space written down directly for us as the span of 2 vectors, the span of the set of 2 vectors, with these in particular being the vectors. S and T are arbitrary parameters, so we're taking an arbitrary linear combination of those 2 vectors. Okay, so if you go through the solution, and there is no free variables, what would your null space be? So let's say that if AX is equal to 0, AX is equal to 0, if we try to solve that, and there's no null space, what is the only solution to that? All right, okay, so let me ask the question in a different way. Oh, okay, so x equals 0 vector. Good, somebody came up with it. So if A inverse exists, then the 0 vector is going to be the only solution. So the null space in this case would just consist of the 0 vector. When you have the situation in the previous problem where you have free variables, your null space is going to be larger than just the 0 vector. So in this case, you could say this is a two-dimensional null space because you can build it as a set of linear combinations of two vectors. Okay, so that's an example of the idea. The null space of a matrix is going to be a subspace of the space where the solutions live. All right, so there's another, okay, so anybody else need more time on this page? Are we good? So the null space of the matrix is the set of all possible solutions to AX is equal to 0. All right, so let me write this again. So the simple case is when the inverse of your coefficient matrix exists, then your null space is just the 0 vector. If there is no inverse for your coefficient matrix, then you look at the solution set right? If the inverse doesn't exist, then you always have the 0 solution. So in this case, in fact, you have infinitely many solutions. So X is going to be I don't know, let's call it vectors Y1. If you have to introduce K free parameters, like we saw with that example we worked out, your answer is going to be of this form. And you can think of the null space as the span of the set of all of these vectors that go along with your free parameters. Okay, so in the previous example, we just had S and T, so there were two vectors involved. We have to take the span of those two vectors. In general, you look at how many free variables you have. That's going to tell you how many vectors you need to be able to build everything in your null set. Okay, so does that make sense, Megan? I see you. Okay, very good. So everybody good? All right, so there's another space that's useful to think about called the column space. It's just a set of all the linear combinations of the columns of the matrix. This is also called the range of the matrix. And that is denoted R of A. If we talk about the column space, we would write that as COL, column of A. Column space of A. Okay, so these are really two names for the same thing. And remember what this actually means. Remember this idea. We could rewrite the system in terms of the columns of the coefficient matrix. So the process of solving this linear system is the process of trying to find the correct linear combination of the columns of the coefficient matrix to get the matrix on the right-hand side. Okay, so the column space of the matrix or the range of the matrix, right? That's a set of vectors. And as long as this right-hand side is in that space, we're going to be able to solve the system. So RHS is the right-hand side. We're going to be able to solve the system as long as this right-hand side vector is in the range of the matrix or in the column space of the matrix. If that vector is not in the column space, then we can't find a linear combination of the columns to build it, so we can't solve the system. Okay, so that's the definition of the column space. Oh, okay, so sorry. SN Seogin, can you tell me what your question was?
I was just telling you to wait on the previous page, but it's already too late. So.
Okay, we can go back. Do you have? I'll give you a minute. Just get what you need, please.
Okay. I'm good now.
Okay, good. So another thing that came in for the comments. So did we prove if the inverse exists, then x equals 0 is the only solution? So yes, we talked about that. So if ax is equal to the 0 vector and A inverse exists, then we can left multiply by A inverse. A inverse times A is the identity matrix. Identity times my vector x is just x. Whatever matrix times the 0 vector is going to give you the 0 vector. So is that clear, Aaron? Do you see why the only homogeneous solution is the only solution to the homogeneous problem is the 0 vector?
Yeah, thank you. Yeah.
When the coefficient matrix is invertible. So Grace, what does it mean if the right-hand side is in the column space? All right, so let me answer that by an example. So let's say we were trying to solve this system. Okay. We could multiply out what's going on here. So we have 0 times x plus 1 times y is equal to a. We have 0 times x plus 0 times y is equal to b. Okay. These are equivalent, of course. And notice that there's yet another way of rewriting the system. X and y now we think of as scalar multipliers of the columns of the coefficient matrix. We're trying to take a linear combination of the columns of the coefficient matrix to get the vector on the right-hand side. Well, I may or I may not be able to solve this. Okay, so when is it that I'm actually going to be able to solve? Well, the vector on the right-hand side with entries A and B has in fact to be a linear combination of the columns of my coefficient matrix. If that's not true, then I can't solve it.
Could you repeat that one more time? You said if what's not true, you can't solve it?
We explicitly have our problem rewritten as a statement that I'm taking a linear combination of the columns of the coefficient matrix. This entry times the first column plus this entry times the second column is equal to the matrix, the vector on the right-hand side. That's a statement of what the system is asking you to do. Produce this vector on the right-hand side as a linear combination of the column vectors from your coefficient matrix. Is that clear?
You're muted.
Sorry, my connection dropped for a second there. All right, am I back? All right, so let me just get rid of all this nastiness. So the point of thinking about the column space is when you have a linear system like this, you can alternatively think of what you're doing with the linear system as you're trying to find a linear combination of the columns of your coefficient matrix to equal the matrix, the vector on the right-hand side, okay? That may or may not be possible. So for instance, here we see, if we simplify things, 0x is 0, 1 times y is y. We need y to be a, and we need b to be 0. The left-hand side of the second equation is identically 0. So as long as your right-hand side is chosen with a b equals 0, whatever the a is, you can solve this. However, if b is not 0, you can't solve the system. Is that clear? Right, I can't solve x. If my system is telling me 0 equals 1, there's a problem. So a way of saying that is that we can solve the system if the right-hand side is in the column space of the matrix. All we're saying let's see here. All we're saying here is that we can solve the system ax is equal to b as long as this b vector, the vector on the right-hand side, is in the column space or the range of the matrix. If it's not in the range of the matrix, as we see here, we don't have a chance of solving. Okay, is that idea clear? Good. Okay. So the column space, just like, or the range, just like the null space, is a subspace, right? That's going to be a set of vectors that in fact is a subspace. And another way of characterizing the column space is that the column space of A, or the range of A, if you like, is the set of vectors B such that AX is equal to B, oops, is consistent. In other words, as long as I can solve AX is equal to B, then that vector B is in the column space. All right, does everyone need more time on this page? Does anyone need more time?
Yes, I do.
All right. Let me know when you're done, Chris.
Could you explain one more time how you knew B wasn't in the column space for the example above?
Well, okay, so let's say that we picked this as our vector. Is that vector going to be in the column space? Well,
No, it won't.
it's not, because y equals 0 looks good, right? The top entries, x times 0 plus y times 1 equals 0. There's no problem there, but x times 0 plus y times 0 is equal to 1, right? That is a big problem. So this particular vector would not be in the column space because you can't solve the system when you put that vector on the right-hand side.
Okay, so if you find one example of it not working, it doesn't work at all.
No, you're sort of not getting the point here. So we're interested in this system for lots of different right-hand sides. Okay, lots of different B's. So we would like to characterize what is the set of all the B's where in fact we can actually solve the system. Well, by definition, the set of all the B's where we can solve the system is the column space of the coefficient matrix. And also by definition, if there's a vector or a set of vectors that when you put them in on the right-hand side and you can't solve the system, then you know that vector is not in the column space.
Okay, thank you. I get it now.
Okay, does that make sense?
Yeah, it does.
We may be looking at one problem and asking, is that vector in the right-hand side in the column space or not in the column space? But more generally, we're interested in trying to characterize for what right-hand sides can we actually solve the system. The set of right-hand sides where the system can be solved is related to the column space. Okay,
Yeah, thank you.
you're welcome. So here's a matrix A. 3, 1, 1, 4, -2, 8. What is the null space of that matrix? And let's try to characterize as a span of a collection of vectors. So what are we going to do? We're going to look at AX is equal to the 0 vector, right? We want to find all the solutions. We're solving the homogeneous version of the problem. The set of solutions is the null space of the matrix. So if I was to multiply X, this coefficient matrix by some vector X, how many entries would that X have to have? Think about AX. We go across the row down the column. X is going to have 3 entries here, right? So let's build this augmented matrix. Notice that we really don't need to carry the zeros along, but why not? Let's do it. So to avoid fractions, I'm going to multiply the first row by 4. So 12, 4, 4, 0. I'm going to multiply the second row by 3. So I get 12 minus 6, 24, 0. Everyone clear on the row operations we did there? Oh, okay. So what are those 2s and oh, okay, so 2s and 3s. Right. So notice every column here corresponds to an entry in the X, right? 3 columns, 3 X's. All right. I want to get a 0 here. So I'll leave my top row as it is. And the second row I'll replace by second minus first. Second minus first, -6 minus 4 is -10. Second minus first is going to be 20. 0 minus 0 is 0. And now let's make my pivots. The top row I'm going to multiply through by 1/12. So 4/12 is 1/3. Second row I'm going to multiply through by -1/10. So I've got two pivots. This is the column for x1. This is the column for x2. This is the column for x3. I'm going to have one free variable. X3 is going to be my free variable. I need more space. So get what you need off of this page. Let me know when we're ready to move on. We good? Okay. So maybe I can fit it up here. So let's try to characterize our solution. From the second row here, if we say x3 is equal to t, we're going to have x2 minus 2t is equal to 0, or x2 is equal to 2t. And then from the first row here, we have x1 plus 1/3 x2. So x1 plus 2/3 t plus 1/3 x3, so plus 1/3 t. 2/3 plus 1/3 is 1. So x1 is equal to minus t. So x equals x3 was t, x2 was 2t, x1 is minus t. So notice we've got the null space of the matrix. Every entry in the null space is a multiple of the single vector -1, 2, 1. Right, so we've explicitly written null space of the matrix A is the span of the vector -1, 2, 1. Okay, does that make sense? Are we good? Okay. Anyone need more time on the page? All right, so let's try another one. Oops. Come on. Okay. So we've got this matrix, we've got this vector B. Is B in column space of A. So in other words, can we pick X and Y oops, darn it. To make this equation true. So that would require that 3x minus y is equal to 2, 2x plus 7y is equal to 4, minus 4x plus 9y is equal to minus 1. Well, that's a set of linear equations. We could solve this by doing Gaussian elimination, doing the elementary row operations to get to the reduced row echelon form. Let's actually just take a more direct approach here. From the first equation, I can see y in terms of x. Y would be 3x minus 2. If I use that in the second equation, 2x plus 7y, so 7 times 3x minus 2 is equal to 4. 7 times 3 is 21, plus 2 is 23. 7 times 2 is 14, so I move 14 on the other side, plus 4 is 18. X would be 18 over 23. And y is 3x minus 2, so let's see, 30, 54. 2 times 23 would be 46. So 4, 8. 8 would be there. So just from the first two equations, I've got a putative solution for x and y. I have to make sure that when I plug those into the third equation, they work. Okay, so minus 4x plus 9y is equal to negative 1. Let's see what I get. So minus 4x will be negative 4 times 18 over 23. 9y, I'll have 9 times 8. So that's 72. 4 times 18. And I've got a problem, right? Negative 4x plus 9y is equal to 0. It's not equal to negative 1. So I could not solve the system. So that vector on the right-hand side is not in my column space. Okay, and if you went through and did this in terms of elementary row operations, essentially what's happening is you're going to get to something like this, where you've got a row that is telling you that there's no solution. All right, so we're almost out of time here. So I'm going to have to ask you guys to take a look ahead at 1.8 and 1.9 in the textbook, Capitula. And I think that's where we have to stop. I don't have time to get started on a new topic today. So you don't have to hang around. If you have questions, I can stay for a little while. So have a good day.
I was wondering, will we ever have to like write a column space Or are we going to be asked if a solution fits the column space?
Well, you might be asked to find the column space. That's certainly a valid question. So to do that, right, we saw how to do that in one of these problems we talked about. Essentially, what you want to do is get a representation of the solution, and from that you can work out what the column space looks like.
Oh, so by that you mean like just assign like random variables for the solution, and then do the same matrix operations, and that's our set of solution, or that's our column space.
Well, probably all right, so directly the column space is just the span of the set of vectors that make up the columns of your matrix, right?
Mm-hmm.
So that is okay. That might not be the simplest way to express the column space. So probably the simplest way to do it is to get the reduced row echelon form of the matrix. And then you can see from that whether there are duplicate columns that you don't have to worry about, and you'll have the columns expressed in sort of the simplest form.
Okay.
You'll be putting zeros everywhere you can in the columns where you have pivots, right? So that's going to make the structure of the column space as easy to see as possible.
Okay.
Okay.
Professor Raymond, I just had a
Yeah.
question regarding the Capitula textbook.
Yes.
So the link that you have on the syllabus, I'm pretty sure this also was an issue for one of my friends, but when I click it, it says access denied. Just when I click the link that you gave us in that little resource.
Okay. Were you logged into UD when you did this?
Yeah, I'm on campus. So if that makes any difference.
Can I ask you, anyone else who's on the Zoom call here, have you tried clicking the link there?
Yeah, I can attest to it as well.
Okay, I couldn't hear what you said, but can you see the Capitula book or not?
I get access denied as well.
Okay.
I had to go to I think the syllabus, like it wasn't on the link that you gave, but in the syllabus, wherever, or maybe files, wherever you have like Driscoll's notes and stuff and his lectures. I clicked on that and it sent me to the textbook.
Oh, okay. So there's some problem with the link, but if you go through Dr. Driscoll's page, it seems to be working, I guess, is the answer. So that's where I'll send you for now. I'll try to fix the link, but you can go through Dr. Driscoll's link, I guess, for now.
All right, thank you.
Thank you.
Okay, have a good day, everyone. Okay, Justine, did you have a question? Okay, I've got to wrap it up for today. Goodbye.